So for today class, I will give an introduction, okay, on the slope stability analysis, okay, whereby you may learn, okay, several subtopic, okay, which is the introduction of slope failure, type of slope, causes of failure, type of failures. Okay. So there will be no what we call as calculations, okay, for this subtopic, for this first week lecture. So by next following weeks, okay, you may learn in term on how to calculate for the factor safety, okay. So your assignment will be based on several calculations, okay. So most probably, okay, I will give the assignment on the third week of this semester. Okay, so next week we may discuss on the course outline, okay, and also on the content of the for the full subject, okay. And for the next following weeks, okay, I will share with you the assignment and the coursework, okay, for my parts, okay. And after the semester break, okay, Prof. Nazri will provide the lecture, okay, and he also will give an assignments, okay, and any coursework, okay. So in total, okay, your coursework or your carry mark, okay, most probably around 60 to 70%, okay, while the rest will be on your final project. Okay, so there will be no a group project. So each of student need to prepare and provide solutions, okay, for each assignment and for each project given to you. Okay. Okay. Yes, I have. The lecture is recorded. Okay. Okay. So any question? You can put in the chat box, okay, if you have any question, okay. So I can answer by read on the chat box during the class, okay. Okay. So a brief introduction on me, okay. So my name is SAFUAN RASHID, okay. So this is an event right after my oral examination, okay. So I graduated from the University of Sheffield, okay, in United Kingdom, okay. I guess most of you not familiar with Sheffield, okay. But when we heard about Manchester or Manchester United, okay, I guess all of you know what is Manchester United, okay. Since Cristiano Ronaldo rejoined again Manchester United, so the team become more and more popular, okay. So Sheffield is about 2 hours, okay, by car, okay, from Manchester, okay. So if Manchester is located at the middle of England, okay, while Sheffield is we call as East Midland, okay, which is on the same what we call latitude, okay, but it is more to the east, okay. So this is my former This is my former supervisor. Okay, this is my external examiner. Okay, well, this is me. At that time, it's very slim. Okay, and this is my internal examiner, Dr. Cripps. Okay, well, this is my co-supervisor. Okay, Dr. Black. Okay, but Dr. Hurt, okay, has retired, okay, and then passed the supervisions to Dr. Black. Okay, so he is the main supervisor, while Dr. Hurt is the former supervisor. Okay. So I have 4 kids. Okay. So at that time, I only have 3. Okay. So this is the eldest one, Omar. Okay, now he is 15 years old. Okay, this is the second one, Usaid. Now he is 13 years old. Okay, at that time, the third one is still in my wife's tummy. Okay, so now she is 10 years old. Okay, so the youngest one is 5 years old. So I have 3 boys and 1 girl. Okay. So my wife is also a PhD holder, graduated from UTM. Okay. Okay. So this is my.
I ask Allah to protect them for you.
Amin, amin. Thank you very much. Okay. So this is my thesis topic. Okay. Behavior of weak soil reinforced with soil columns formed by the deep mixing methods. So it is a part of what we call as ground improvement method. Okay. So I did this study using a small scale physical modeling. Okay. Then I came up with a method, okay, to determine the failure mechanism, okay, of the foundations, okay, and also for the treated soil deep mixing methods. Okay, so this is the dissection diagram, okay, of column failure patterns. Okay. Okay. So now we're back to our business. Okay. So actually, I have revised the slide. Okay. So please get the new version. Okay, in the e-learning. Okay. I have updated this a late morning. Okay. Around before the afternoon. Okay. So I have upload in the e-learning. Okay. So you may use that the latest version, but without my introduction of me. Okay. Okay. So slope failure is the movement of mass on slope. Okay. So the term is slope and also the mass. Okay. So there will be a movement of mass, okay, on a slope or on a sloping structure. Okay. So if it's a flat, so we may not consider it is a slope structure. Okay. So the type of movement, okay, either force, slides, flow, topple, and several movements. Okay. All of them we consider as a slope failure. Okay. So several authors has differentiated, okay, between the landslide and slope failure, okay, due to the area, due to the slope degree, okay, and also due to the movements of the event. Okay. For instance, for the landslide, it involves an extensive area. Okay. my slopes, okay, which is less than 20 degrees, okay, and the movement is slow, however, it is gradually moved. Okay. While for the slope failure, okay, it is a localized failure, okay, under a very limited area. Okay. So normally happen for the steep slope structure, and the movement is fast, okay, sometimes with no sign, and usually it is happen due to the high intensity of rainfall. Okay. So the stability of the slope should be evaluated when slope movement due to additional loads or loss of strength is identified to cause problems. Okay. So as an engineer, so we need to understand first on how to evaluate the slope movement, and also on how to determine the stability of the slope. Okay. And also we need to identify what is the factor that cause for the slope to fail. Okay. So first we need to check the stability. Okay. So at the same time, we need to identify what is the cause factor that contribute for the slope to fail. Okay. So this example of the slope failure, okay, where we have fall, toppling, spreading, sliding, and flowing. Okay. Okay. Normally for the soil slope, okay, we may discuss on this type of slope movement or soil movements. Okay. So in this particular topic or in this particular subject, all of our discussions are based on this sliding movements. Okay. However, I will discuss a little bit on the fall, okay, toppling, where toppling is normally occur on the rock slope structure. Okay. So for the spreading, okay, is normally happen, okay, due to the infinite type of slope, okay, where we also may discuss in this topic as well. Okay. So this we call as a finite type of slope because the slope structure has toe and top. Okay. While for the flowing, it more related to for example, a debris flow. Okay. If I'm not mistaken, last month, okay, we have a debris flow event at Kedah, okay, in Yan, okay, specifically, okay, where there are a huge debris flow, okay, occur, okay, at that particular area, okay, and have involved, okay, in the study to develop what we call as a check dam or sabo dam. Okay. So the government will build a sabo dam, okay, in order to minimize the problems, okay, due to this debris flow event. Okay. So this is the explanations, okay, on the event of failure. Okay. For example, for the fall, okay, this is the detachment of a soil and or rock fragment that fall down a slope. Okay. So normally, a lot of event happen on the rock fragments. Okay. And there are some analysis that can be carried out, okay, to determine the rockfall, okay, due to the mass of the and the volume of the rock. Okay. So topple, this is a forward rotations of a soil and or rock mass about and axis below the center of gravity of mass being displaced. Okay. So normally this is due to the weathering process, okay, where the joints of the rock, okay, became weak, okay, so they have a potential, okay, to topple, okay, due to the rock mass is very high. Okay. So slide, this is a downward movement of a soil mass occurring on the surface of rupture. Okay. So normally we use a circular failure analysis, okay, to determine the stability of this slide due to the slide failure. Okay. So the spread is the form of a slide by translation. Okay. Because when we look on the figure, okay, we found that they are a weak formations here. Okay. So due to these weak formations, okay, so they have a potential of this spread happen. Okay, it occurs by sudden movement of water-bearing seams or sand or seep of verlin by clay or loaded by fill. Okay, so this is a very problematic soil. Okay, where they have where it has been exposed by a water. Okay, so the last one's flow. This is a downward movement of a soil mass similar to a viscous fluid. Okay, so means that due to for example heavy rain event, okay, so the soil has been exposed, okay, to the water, okay, and then it become like a fluid or liquid, okay, so then and it start to move downwards. Okay. So type of slopes, okay, natural slopes and man-made slopes. Okay. So as we know, natural slopes is a formation of hill and valley. Okay. So it is a long-term process and short process. However, the short process is, I guess, more than 100 or 1,000 years or million years. Okay. When we do or when we disturb the natural slope, okay, so we consider it is a man-made slope. Okay. For example, we do an excavations, okay, on the slopes, okay, because we want to build, for example, a roads. Okay. So in that sense, we may consider it is a man-made slopes. Okay. So this is an example. Okay. This green dash green line, okay, is excavation part, okay, where actually this dash green line is the actual formation elevations of the natural slopes. Okay, so because due to the developments of that particular area, so they need to excavate the slopes. Okay, so when we touch or when we disturb the slope, so the factor safety value will be differ compared to the natural slopes. Okay. And then we have another one we call as a slope of embankment and earth dam. So this is not actually a natural slope. Okay, it is a construct slopes. Okay, for example, when we want to build a highway, okay, or a roads, which is the road level should be higher than the existing level. So we need to construct an embankment. Okay, so this example of a slope or embankment slope. Okay, so this is considered as a embankment. Okay, so this is the slope that need to be analyzed, okay, to check the stability of this slope. Okay. At the same time, to check the stability of the whole structure, okay, so we should check the bearing capacity of the soil. Either it can cater for the load applied on the soil. Okay. So normally for the slope of embankment, okay, we should design 1/2, okay, which is 1 vertical, 2 in horizontal. Okay. In terms of degree, it is 27 degree. Okay. Because that is the most ideal slope gradient, okay, in a stable conditions. Okay. So the next is the earth dam, okay, used, okay, to make a reservoir for water. Okay. So this is the earth dam structure. Okay. So need to be built, okay, with a same approach with the slope embankment. Okay. So either it made from a soil, okay, but when we call earth dam, it is made from a soil. Okay. So there will be another dam that made from a concrete structure. Okay. So this dam is not huge as a concrete dam. Okay. However, we need to check the stability of this dam, okay, by including what we call as a seepage, okay, because the water will penetrate or transmit inside this earth dam. Okay, so we need to run the analysis by consider the seepage parameter. Okay, compared to the slope of embankment, so it is not necessary, okay, to carry out for the seepage. Okay, first, due to the groundwater level is far. Okay, but if we are interested to look on the stability due to the rainfall, okay, so we need to include the rainfall infiltrations inside the analysis. Okay. So for the slope terminology, okay, so we have here the height of the slope. Okay, first this is a finite slope. Okay, so I will discuss next week. Okay, the type of the slope in terms of their geometry. Okay, so in this case we call as a finite slope. Okay, because it has toe, it has, and it also has the top. Okay, so the height of the slope, and then there is the toe. Okay, the lowest level of the slope geometry. Okay, then slope ratio. Okay, a typical slope ratio is 2:1, okay, which is horizontal to vertical. Okay, and it's very weird to use 1:1, okay, because 1:1 is 45 degree. Okay, so unless it is a natural slope, so we can cut into 1-to-1. However, for the embankment, because we need to compact the soil later on, so it is safe to design or to build 2-to-1 slope ratio. Okay, so then we have a terrace. Okay, this is a US term. Okay, in UK term, they call as a berm. Okay, BERM. Okay. Then this is the surface or face, slope surface or slope face. Okay. Okay, the top or scrub is the top of the slope. Okay. And we have, or they will apply a surcharge. Okay. For instance, if they want to build or construct for any development on the top of the slope. Okay. However, it should refer to the authority, okay, to check, okay, what is the distance, okay, of any structure to the slope, top of the slope. Okay. So for example, for the terrace, okay, for every 6 meter height, okay, should have a one berm or one terrace. Okay. For example, if this case, okay, I guess the total height of this slope is around 12 meter. Okay, so for the first 6 meter, okay, so the designer or the developer should have a berm. Okay, so normally the width of the berm is around 1.5 to 2 meter width. Okay, so easy for the any constructions vehicle, okay, to do the trimming, okay, because they have enough or surface width, okay, to park their to mobilize their vehicle on this berm. Okay. So this is the slope terminology. Okay. Okay. So principle of slope stability analysis. Okay. We look on one we call as one block, okay, of a soil. Okay. So sliding will occur if the shear stress developed exceed the corresponding shear resistance of the soil. Okay. So in this case, failure is assumed at a certain plane. Okay. So this is the plane. Okay. So this is the alpha. Okay. So the weight of the block we consider as a W. Okay. So this we consider as W. Okay. So in order to find what will be the driving factor, okay, so the weight has been resolved to sine alpha. Okay. Okay. While the reactions on the plane, okay, we consider as a shear resistance. Okay. So the ratio between the shear resistance and the shear stress, okay, is called as a factor of safety. Okay. So in that case, the factor safety doesn't have any units. Okay, it is a dimensionless. Okay, because we divide stress with stress, or some cases we use the moment concept. So we divide moment with moments. Okay. So for the natural slope, okay, the factor safety should equal or greater than 1.25 to 1.4. Okay. So meaning that if we design or we want to do and we carry out for the analysis, okay, we need to make sure that the factor safety should greater than 1.25, okay, or should go for 1.4. Okay. So for the man-made slope, okay, where the slope we have disturbed or we do some trimming, okay. So we need to make sure that the factor safety should greater than 1.5. Okay. So that is the specifications, okay, that usually been used in Malaysia, okay, under the public work department or under the any authority. Okay, a simple analogy here. Okay. Okay, there are two different material, okay, unconsolidated sediments and a sandstone. Okay. So I just want to show how this analogy describe the principle of the slope stability analysis. Okay. So what hold the sediment in place and what hold it down? Okay. So we put in a block type analysis. Okay. We have here the degree of the slope in theta, and we may assume this block has a width of W. Okay. So then we put in a diagram. Okay. So the weight is concentrated at the center of the block, which is the center of the mass. And the theta is the slope angle. Now we focus on the W. Okay, weight always point straight down, okay, due to the gravity. Okay. Then the weight actually is the force. Okay. So then we resolve it into FP, okay, where the component of the weight parallel to the slope. Okay. So in that case, we should refer for the theta value. Okay. So that is the slope angle, okay, based on the trigonometry. Then the FP is considered as W times sine theta. I guess during your secondary school, especially for the Malaysian student, okay, you have learned, okay, on the trigonometry, okay, on how to determine the sine, tangent, cos. Okay, so during my time, when I was in Form 5, okay, 1998. Okay, so you can estimate how old are me. Okay, so my teacher teach a simple wording. Okay, for example, for cos is sine, cos, and theta. Okay, so in Malay we use T tentang, okay, opposite, and H is hypotenuse, okay, and S is CC, adjacent, okay, while H is hypotenuse. For the tangent, T is tentang, opposite, and S is adjacent, CC. Okay, so we simple wording, saya tak hafal. Kalau saya hafal, tentu tak susah. Okay. So I still remember and use until now. Okay. Okay. So then we get W sine theta for the FP. Okay. So the force parallel to the inclined plane, which is FP, is what pull it down the slope. Okay. So we call it as a driving force. If we refer to the Bishop or Morgenstern and Price or any method of slices, they call as a driving moments. Okay. Okay, so that is for the FP. Okay, so the small angle, the small pulling force, okay, while the large angles is large pulling force. Okay, as a rule of thumbs, okay, you can estimate the stability of the slope, okay, if the friction angle of the soil is greater than the slope gradient. Okay, so I guess most of you know what is the phi or phi. Okay, should greater than the theta. So typically, the slope, the soil internal friction angle in effective, okay, is around 20 to 30. Okay, so that's why the degree of 1 to 2, okay, which is 26, can consider as a stable slope conditions. Okay. So for a large angle, so it can produce a large pulling force. Okay. Okay, slope mechanics and material strength. Okay, so now we try to include, okay, the material of the soil, okay, in determine the stability of the slope. Okay. Previously, we discussed on the driving force. Okay. Now, we may look on the resistant force. Okay. So, the Fn is the normal force, okay, towards the plane, okay, of the slope plane or the failure plane. Okay. So, then we gain W cos theta. Okay. So, this W cos theta actually would help prevent for the soil to move downwards. Okay. So the component of the weight normal of perpendicular to the slope, okay, which is the Fn. Okay. So the normal force is what contribute to the force, the resist movement down the slope. Okay. It in part control the material strength. Okay. So when the block is horizontal, okay, where the theta is equal 0, then Fn is equal to W, because cos 0, it is 1. Okay. Okay. So the friction force FF, okay, is equal to Fn times with the coefficient of friction. Okay. The coefficient of friction quantifies the degree of the roughness between the two surfaces, bottom of the block and the horizontal surface. So low coefficient of friction if the block is smooth and the surface also is smooth. Okay. High coefficient of friction if the rough block, if the block is rough and also the surface block is its surface is also rough. Okay, so there is a simple explanation there. Okay. So then the coefficient of friction change with geologic material, okay, where clay is less in terms of friction compared to the sand and broken rock. Okay. So the Greek symbol mu is usually used for coefficients of frictions. Okay. So the coefficient of friction also controlled by the mineralogy. Okay, quartz is strong, olivine is not. Okay, this is the type of mineralogy in the soil material. Okay, so the green shape, angular, is more has a higher friction compared to the round surface or shape, and the packing arrangements. Okay, a loose is less friction compared to the tight packing. Okay. So there is several explanations on the coefficient of frictions. Okay. So the magnitude of an Fn increase the interlocking of the two surfaces because the force push the imperfections together, making it harder for the block to slide. This increase the friction force. Okay. So the magnitude of the Fn increase the interlocking of the two surfaces because the force push the imperfection together, making it harder to the block to slide. Okay. The higher friction force, okay, is due to the higher of the block width or force, normal force. Okay. So the magnitude of Fn increase the interlocking of the two surfaces. Yeah, I guess it's a repeat just to show in terms of when we increase the block width or we decrease the gradient of the slope, so it may contribute to a higher normal force. Okay. Yeah. So increase, if this increase, okay. So if the Fn is increased, the friction force will be increased, or if the coefficient of friction is increased, the friction force also increase. Okay. So it contribute by two parameter there. Okay. Okay. Mechanical friction keep the block from sliding. Okay. So actually the friction, the coefficient of friction actually contribute from the internal friction angle. Okay. That normally as a strength parameter of the soil. Okay. So molecular cohesions between the grain also contribute to the material strength and keeps the block from sliding. Okay. So a part of that, we also have the cohesions. Okay. The cohesions between the soil particles, okay, that provide for the increment of the friction. Okay. So moist sand has a strength. Okay. So these are some example there. Okay. So if a dry sand, so it's not easy for us to remove this structure, okay, compared to a moist sand. Okay. So the strength is created by molecular force of attraction between the sand, water, and air. Okay. So this is another example between the calcite and silica cement that bind mineral together in another form of molecular cohesions. Okay. So the stability of the slope is analyzed by comparing the magnitude of the driving force to the resisting force. In that case, the number of the factors of safety is derived from the ratio of resisting force with the driving force. Okay. So mathematically, okay, so when we want to calculate for the factor safety, so we may use this formula. Okay. So actually the C, okay, if we use the more column equations, okay, so we may include the phi value as well. Okay, we may discuss later on. Okay. So while for the W sine theta is actually the driving force where it consists of the weight of the soil or the block, okay, which is parallel to the plane of the failure. Okay. So that is the principle of the slope stability analysis. Okay. So how they come up with the factor safety equations. Okay. Basically based on the resisting force and also from the driving force. Okay. So at low slope angle, Fp is small and Fn and hence Ff are larger. Okay. So the factor safety is greater than 1. So actually, this is based on a limit equilibrium approach. Okay. So if factor safety is equal to 1, okay, means that the friction or the resisting force is equal to a driving force. Okay. So we also consider it is a critical conditions of slope stability. Okay, you just imagine if the factor safety is equal to 1 and suddenly an additional loads apply on the slope structure. So it may increase the driving force and it may reduce the factor safety less than 1. So suddenly the slope will start to move, okay, and it is may contribute problems, okay, to the residents or to any people that live nearby the slope. Okay, so that's why we need to design for factor safety greater than 1.5. Okay. So at a high slope, Fp is large and Fn and hence Ff are smaller. Okay, so that is the logic. Okay, so to be on the safe side, okay, we need to make sure that the gradient is low as we is low as it can. Okay, okay, to make sure that the slope, the factor safety is greater than 1.5. Okay. Okay. So the slope fail if Fs is less than 1. Okay. But to be on the safe side, the Fs should greater than 1.5 as I mentioned before. Okay. Okay. So can we take a rest for 5 minutes?
Okay.
Yes, okay. Okay.
Yeah, because I need to stop the recording. Otherwise, I need to have a large storage, okay, to upload. the first, if I continue until 2 hours. Okay, so I stop first. Okay, so